Let's welcome the speaker of the third paper, which is Diego Biagini, on the paper entitled HieraSurg, Hierarchical-Aware Diffusion Models for Surgical Video Generation. Welcome.
Test. Good morning, everyone. I'm Diego, and today I'm presenting to you my work, HieraSurg, Hierarchical-Aware Diffusion Model for Surgical Video Generation. As the previous presenter has already outlined, video generation has become quite an accessible area of research, and it has been applied to a variety of domains, including the surgical one, and in particular, internal surgery, like laparoscopy. Here you see a couple of works from last year and this year, where they tried to train latent video diffusion models on the task of surgical video generation. And why do we do this task? Well, the reasons are twofold. The first one, for data augmentation, to generate variations of existing videos, maybe to upsample rare cases and then train better downstream models. And the other, less talked about, is using these models as kind of word models with the ability to anticipate the evolution of a scene, in this case, a surgical scene. When we look at the current state-of-the-art general-purpose video generation models, like VO3 or One Video 2.2, like the one that generated the sample on the left here, we see that they have amazing visual quality. And here, even though you can't tell it, it's supposed to be a laparoscopy, and it's not a laparoscopy, but I guess that's not in the training data. But anyway, so you see a great visual quality, which is kind of cinematic, but that's not really what we need when we generate surgical videos to use in downstream tasks. What we want is for these videos to be able to be generated through and be able to follow procedures and have clear semantic entities that interact with each other, like tools interacting with anatomy. Let's focus on a particular type of surgery, laparoscopy cholecystectomy, and we have an amazing data set for that. That is called T50. Videos in this data set can be segmented into surgical phases, like clipping and cutting, and events that happen in these videos can be labeled according to triplet labels, like scissors, cut, grasper, retract, gallbladder, and so on. And this tells us what is happening frame by frame. So both of these type of information are semantic information that describe a certain amount of the surgical scene. We could think of putting it in a hierarchy of how much of the scene they describe, like in the sense of the length of the video. And at the top, we would have the phase. It describes something kind of general that happens for 5, 10, 15 minutes, depending on the phase. After that, we have the triplet labels that describe what happens in a shorter time frame, like 5, 10 seconds. But after that, there is an additional semantic information that we can come up with, and those are semantic segmentation maps, frame by frame. They tell us where entities are, how they are spatially, and maybe semantically related to each other. So how do we use this supposed hierarchy for our video generation? That's what we try to do with our work. And so we leverage it by splitting the video generation process into 2 stages. In the first one, we have a latent video diffusion models that takes in input an initial state, so the first frame of a video, the first segmentation map, and high-level surgical information, like phase and triplet information. And this model, and we call this model semantic to map, S2M. Its objective is to predict the evolution of the scene in segmentation map space. Then we have a second stage model called map to video, which is able to bridge the gap between segmentation map space and video space. It's still a latent video diffusion models, but trained on this other task. A few more details about the architecture, like how do we provide the surgical information. Use a pre-trained surgical VLM, like Pesca VLP, to encode the triplets and phase separately, their textual representation, then condense them over the time dimension and inject them into the first stage model. As for how the initial state is given to both of the models, we encode the initial frames using the usual approach of encoding them through the VIE and stacking them with the noise latents. And an additional detail on the first stage model, we don't use, when we encode for the latents. We don't use the VIE in video mode, but in frame mode. We encode frame by frame and stack them before noising them so that we don't have compression along the time dimension. Another important detail is how we get between the first stage and the second stage. There is an additional detail, and that is due to the fact that the output of the first stage is the output of the decoder of the VIE. And so it won't necessarily give out perfect semantic segmentation maps. They need to be post-processed so that they don't have a huge variety of colors. So we use a clustering procedure of the space of colors and map these to a smaller set of discrete colors. Without further ado, let's go to some results. For the second stage model, so we give it an input segmentation map above, and below you see the visual results. To obtain this model, we fine-tuned a cogVideoX to be text-to-video backbone by replacing the textual conditioning with the segmentation map conditioning. The segmentation maps are given at 1 FPS. The video is generated at 8 FPS. And for the first stage model, and now it gets connected to the second one, this is, as I said, what to give to the first stage model. To the left, you see we give it the surgical information, so the phase and triplet of the next frames, then segmentation of the first frame and the video, and the first frame of the video. And we ask it to generate an evolution in segmentation map space. Then we give these results to the second stage model. And to the right, you see what you get when you provide the predicted segmentation maps. To the left, use the ground truth with the second stage model. And they have slightly different evolutions. This is another sample where the first stage model predicts an additional entity, an additional tool. And the second stage model is able to correctly add that to the generated video. As far as quantitative results, we evaluate the visual quality of our videos using the usual fidelity metrics like FED, FID, and we outperform previous metrics on this domain. But we also introduce an additional set of metrics based on detector agreement. So we train a yellow V8 detector on the task of surgical tool detection. And what we do is we take a real video and a generated video. And in a frame of the real video, we look for tools found in it, and we look at whether in the same frame in the generated video, in a close enough position, there is the same tool. If that is the case, we have a hit, and we aggregate this over the entire number of frames, all the frames, and we call this the hit rate. What these metrics tells us, if we only evaluate it for the second stage model, so we provide the second stage model with input segmentation maps, what these metrics tell us is the ability of the second stage model to follow the conditioning. But if we evaluate it for the entire pipeline, what this tells us is the ability of the first stage model and then the second stage model that brings it to video space, the ability of this entire pipeline of predicting the evolution of the scene as far as tool segmentations go. And we get some initial result about its ability to give at least an evolution that makes sense with respect to the initial video and conditions given by the surgical information. To conclude, what we managed to obtain was a surgical video generator of great visual quality, which can either generate video starting from dense scene information like semantic segmentation maps, or can first generate semantic segmentation maps using the first stage model and then bring this to video space. So this gives us kind of two models in one, the ability of either using only the second one if you have this more fine-grained information, or use the entire pipeline if you only have abstract information. And we also saw some predictive capabilities of the entire pipeline, at least as far as the short-term prediction goes. But there is still a way to go to have reliable video generations that can be used in the wild and to train better downstream models. For example, in particular for the first stage model right now, it only takes these sparse triplet labels and high-level surgical information, which is just not enough to have reliable prediction of the future state of the surgery, more than a few seconds, and considering the current state. So improvements could be made by injecting into the generation more complex expression of surgical actions and surgeon intent. Another direction of improvement is making everything more interactive, leaning even more into the domain of word models, kind of having something like completely data-driven simulator where the surgeon can play with it, it's given an initial scene, and through real-time controls can manipulate maybe tools, and the underlying word model, generative model, can see the effects that those actions have on the scene and visualize it for either the surgeon or any other diagnostic task. With this, I would like to conclude. Thank you for listening, and I hope